Okay, now let's say something about Gaussian quadrature. And let me sort of just give you a little bit of intuition, right? So when we talked about, say, the Newton-Cotes formula, we had looked at a case where we had quadrature formulas where the sample points where we sample the function are uniformly spaced, okay? And then what we found basically was that if you had n plus 1 points, right, then you would, in general, it's like be able to exactly integrate polynomials up to degree n. Okay, and that's not so surprising because a polynomial of degree n has n plus 1 coefficients, and if n plus 1 points, then there's sort of n plus 1 constraints, which then allow you to determine the coefficients of the polynomial. So all that's sort of relatively consistent. But let's ask then the following question, which is that if now I allow you to choose not just the weights of the quadrature rule, but where I evaluate the functions, can I do better? Okay, because in principle now, if I allow you to choose both the weights and the quadrature points, I've doubled the number of free parameters that's like in my algorithm, and maybe that allows me to get a quadrature rule which is more accurate. So the idea, if you will, is that can we choose both the quadrature points and quadrature weights in a smart way, in a good way, so that the quadrature rule is exact for a larger family of polynomials, right? Okay, so that's sort of the intuition, if you will. Okay, so you want to maximize the degree of precision of the quadrature formula by allowing yourself the flexibility to choose both the weights and the points. Okay, so there are n plus 1 nodes, right? So which go from x0 to xn, and there are n plus 1 weights. So you have 2n plus 2 sort of parameters, if you will. So as you know then, well, as what you would like then is that you would like to have to take advantage of the freedom you have in choosing these 2n plus 2 parameters to then have the quadrature rule be exact, right? On polynomials which depend on up to 2n plus 2 parameters, which are polynomials of degree 2n plus 1. So can we make this exact for all f of x which are in polynomials of degree 2n plus 1 on x? So now let me make the observation, which is that if you know what the quadrature nodes are, then of course you can use the Newton-Cotes algorithm or the Newton-Cotes formula to figure out what the weights are. Okay, so the hard part, if you will, is in trying to figure out what the nodes are in order to have this property that it's exact for all polynomials up to degree 2n plus 1. So let me make the following claim, it's like which I will first state without proof, and then we'll see how later it's like in the proof of the, it's like the degree of precision of the Gaussian quadrature formula we'll see how this property shows up. Okay, so let me make the following claim. Claim is that the nodes, right, the optimal nodes, if you will, are obtained from the roots of the maximal degree orthogonal polynomial. So what do I mean by that? So let me perhaps illustrate this idea with an explicit example. So let's look at the n equals to 1 case. Okay, so n equals to 1, right? So these has 2 nodes and 2 weights. Okay, so I want to find a quadratic orthogonal polynomial, right? So let's just write this as p2 of x is equal to x squared plus ax plus b, right? The constant scaling in front doesn't really matter because I'm really just interested in the roots of this orthogonal polynomial, so I'm going to normalize it to 1. Okay, and what it means for this polynomial to be orthogonal is that there's this idea of an inner product between, say, 2 functions f and g, given by some integral of f of x times g of x dx over some appropriate interval. Okay, and the way you should think about this is that this is, morally speaking, the infinite dimensional generalization of the dot product, which you might have seen in linear algebra, right? So in linear algebra, you have 2 vectors. You take this sort of component by component product and you sum it all up. And this is sort of the same thing in some sense. You can think of the function as being like an infinite dimensional vector. You're multiplying, it's like the corresponding components of this infinite dimensional vector, and instead of summing it up, you're integrating it, right? So there's a real sense in which this integral is like an inner product, or it is an inner product. Okay, so with that in mind, what we want for this p2 of x, right, is to have the following property. You want that p2 of x is orthogonal with respect to this kind of inner product to lower degree polynomials. So this is a polynomial degree 2. You want it to be orthogonal to polynomials of degree 0 and polynomials of degree 1, right? Okay, so so you want that the inner product between 1 and p2, right, to be 0. This is the integral of just p2 of x dx. And then for purposes, for simplicity and sake of exposition, I'm going to consider a sort of interval of integration which is symmetric about the origin. That makes your life easier. So I'm going to look at an interval from -1 to 1. Right? So I want that p2 of x is orthogonal to 1, so p2 of x is basically being multiplied by 1. And then I integrate it from -1 to 1 and want it to be 0. And I also want, x inner producted with p2, which is just the integral from -1 to 1 of x p2 of x dx is equal to 0. Okay, so so you can evaluate what this is. It's like for p2 is equal to x squared plus ax plus b, right? So this is the integral from -1 to 1 of just x squared plus ax plus b dx. All right, and this is equal to 2/3. I'm going to skip a few steps, but it's 2/3 plus 2b. All right, on the one hand, and this is equal to the integral from -1 to 1 of x cubed plus ax squared plus bx dx. Okay. Actually, before I do that, let me solve for b here, right? So 0 is equal to 2/3 plus 2b. This implies that b is equal to -1/3. So I can substitute it here. right? So this is minus 1/3 x. Okay, and that is equal to 2/3 a. So this implies that a is equal to 0. Okay, so the relevant orthogonal polynomial, which we have then is p2 of x is equal to x squared minus 1/3. Okay, all right, so, and this has the property that, again, p2 of x times 1 integrated from minus 1 to 1 dx is equal to 0, and the integral from minus 1 to 1 of x times p2 of x dx is equal to 0. Okay, all right. So that's uniquely defines. It's like this family. It's like of orthogonal polynomials, because if you think about it, again by linearity, the orthogonal polynomial is only defined up to a scalar multiple, right? So because if you have something like this is satisfied if you replace p2 with lambda p2, this integral will also clearly be 0. So that, you know, there is an overall scaling. It's like symmetry of the problem. Okay, so anyway, so you get this p2, right, which is x squared minus 1/3, and then the roots of that, so the roots of this are 1 over square root of root 3 with a plus minus sign. Okay, so the claim is that that's what you want to use. It's like as the nodes of your Gaussian quadrature rule. Okay. Okay. And then once you have those roots, you can compute the coefficients. Okay. So I want to consider some approximation of the integral from minus 1 to 1 of f of x dx by sort of a0 f at minus 1/3, minus 1 over square root of 3, right, plus a1 f evaluated at 1 over square root of 3. Okay, and then you can use the method of undetermined coefficients. Sorry. And if you use the method on determined coefficients, it's like you get that a0 is equal to a1 is equal to 1. So the formula, the corresponding sort of Gaussian quadrature rule, it's like for n is equal to 1, right, is equal to just, this is approximately equal to f at minus 1 over root 3 plus f evaluated at 1 over root 3. Okay. All right. So that's sort of a brief example of this, and then I'll stop here, and then I will prove it's like some additional results about Gaussian quadrature in a little bit. In particular, sort of this notion of degree of precision of the method.